My name is Mayank Vadhavan, and this is the presentation for my final project in wireless communication course. The title of my project is Analysis of Different Error Correction Codes. So basically, in this project, I have analyzed different error correction codes and error detection codes. I have plotted the bit error rate versus signal to noise ratio for various error correction codes. I have also mentioned the application of various error correction codes and their shortcomings. So basically, wireless links are more susceptible to noise or errors than wired links, which makes error detection codes and error correction codes crucial for reliable communication. Error detection codes are used to determine if an error was occurred during transmission. So if the data was corrupted, the sender transmits the data again. So this happens when there is a back channel. Whereas error correction codes can recover corrupt data even when there is no back channel. So the topics which I would cover in this presentation would be existing literature, introduction, error detection codes, error correction codes, applications, results, conclusion, and project demonstration. So this slide tells you about the existing literature. I found many research papers online, which is very closer to my work in this subject. So the first paper is LDPC code construction with flexible hardware implementation. So as the name suggests, it explains LDPC for hardware implementation. Second one is improved decoding of Reed-Solomon and algebraic geometric codes. So basically this paper describes a way to improve the decoding for Reed-Solomon codes. The third one is a normal ARQ scheme applied to wireless communication. This one shows how ARQ can be used for various wireless transmission techniques. The fourth one is development of turbo and LDPC codes for deep space application. It just explains how the turbo codes and LDPC codes are being used for deep space communication and satellite communication. And these research papers explain error correcting codes in very specific situations, and this really makes it hard to compare all these codes in a more general form. Yeah, so when data is transmitted over a wired or wireless links, errors are introduced in because of channel noise. Error detection codes used to check errors during transmission, and error correcting codes help the receiver to recover the corrupt data even when there is no back channel involved. So in this presentation, I will go in briefly about four error detection codes: parity bits, repetition codes, checksum, and cyclic redundancy checks. So in checksum, parity bit is one of the most simple error detection codes. So in this example, a parity bit is added to a 7-bit binary number, which results into an 8-bit binary number. I'll just give you an example about the first row, 10111010. So number of ones in this is even. So the parity bit in case of even parity is 0, and the parity bit in case of odd parity is 1, because we have to make number of ones even in case of even parity and number of ones odd in case of odd parity. So we can put the parity bit as 0 or 1 in either of these cases. So in case of repetition codes, for example, in case of 4-1 repetition code, blocks are sent 4 times. So for example, for 011, it is sent like 011 4 times. So if any of the blocks is different from the other, then we just show that it's an error. And at the receiver, we can decode this by majority vote. So the advantage of this is that it is a very simple error detection code, and the disadvantage would be that this method is very inefficient because the data is being sold multiple times. And if a bit flip happens at the same place for all the blocks, then this error detection code would not be able to detect the error. So the next one is like checksum, and these are the steps of performing the checksum. So the first step would be we compute the checksum of the data using a checksum function. This checksum is sent along with the data. The receiver separates the data in the checksum, and it uses the same checksum function to determine the new checksum. Then we compare these two checksums to see if there was any change in the data. So if the two checksums are different, then the data which we have received is corrupt. The next method is cyclic redundancy checks, and these are 5 steps to do it. We use a generator polynomial to perform long division on the data. So the generator polynomial in this case would be a divisor, the data would be the dividend, and the remainder will be used to detect for errors. So the remainder and the data are sent, and receiver can use the same generator polynomial and the same data to find a new remainder, and these two remainders are compared to see if an error was introduced. So if the remainders are different, then there was an error, otherwise it wasn't. And the next method is using cryptographic hash functions. So we can use a cryptographic hash function at the sender and at the receiver to find the errors. And the cryptographic hash value is unique, and the chances of collision are very less. And if we use a secured cryptographic hash function, then it becomes very hard to crack it as well. Now I'll discuss error correction using ARQ. So this is generally used in case of network application, and this is widely used in internet. And error correction using ARQ is of three types. First is stop and wait, and second one is go back, and third one is selective repeat. I won't go into details of all this in this slide. So now this slide is about error correction codes, and these are also called forward error correction. And four codes which I have discussed here are Reed-Solomon, LDPC code, turbo code, and BCH codes. So this is a Reed-Solomon encoder and decoder. So in case of encoding, we add a redundant data to the data message. The message is then sent through a communication channel, and the receiver decodes the data using Reed-Solomon decoder. The Reed-Solomon code word looks like this. So the total number of bits are n, and k is the number of bits in data, and 2t are the total number of parity bits. And Reed-Solomon can detect 2t bits of errors, and it can correct up to t bits of errors. So these are the application of Reed-Solomon codes are generally in the data storage disk like compact disk and CD and DVD. They are also used in barcodes and space transmissions. The advantage of Reed-Solomon is that it's very easy to code. However, they are being replaced by turbo codes recently. So now I'll discuss low density parity checks. So this is an example of a LDPC code in the figure attached, and LDPC codes are made using sparse bipartite graphs. LDPC decoders are iterative algorithms. That is, in each iteration, the message is sent from the message node to the check node, and then again from the check node to the message node. So the advantage of using LDPC code is that encoders and decoders are very fast, and the application would be they are used in space communication and satellite communication as well. So now I'll discuss turbo code. The performance of turbo codes are similar to the LDPC codes, and they are like very close to Shannon limit. And turbo codes are currently competing with LDPC codes for high-end applications. Interlevers are a big part of turbo codes. The advantage of interlevers are that they give very good performance. The disadvantage is that it makes the decoding process very slow. And like I discussed, the turbo code applications would be in 3G and 4G mobile, and they are also used in satellite communications. Now I'll discuss BCH codes. The application of BCH codes are in storage devices like CD, DVD, and solid state device. They are also used in satellite communication and two-dimensional barcodes. The advantage of BCH codes are that they have a very simple design, and you can control initially at the time of the design how many symbols you want to get corrected. So that can be decided way early on. Now I'll discuss convolution codes. So these codes can work on symbols of any length, and it doesn't have to be fixed length like the block codes which I have discussed earlier. So basically these are the block codes, and this is different, convolutional codes. So data encoded using convolutional codes can be soft decoded using a Viterbi algorithm, and this is a dynamic programming algorithm, Viterbi. And convolution codes have many applications. For example, in speech recognition, GSM, CDMA, satellite communication, and also in bioinformatics. So basically, I have compiled the applications of all these codes. I have mentioned the wireless links on the left side, and which codes are generally used for these applications. For example, for 2D radio, two-way radio, ARQ codes are used, and the four codes, Reed-Solomon, LDPC, turbo code, and BCH codes are not used for this one. For satellite TV, Reed-Solomon, LDPC, turbo codes, and BCH codes are used, and ARQ is not used. In case of Bluetooth, only ARQ used, and the rest of them are not used. For CDM and GSM, all of them are used. For 3G, 4G, and GPRS, ARQ is not used, and similarly for satellite and deep space, ARQ is not used. So Reed-Solomon, LDPC, turbo, and BCH codes are used in satellite communication and deep space communication. So these are the results of my code, which I've done in MATLAB. I will explain this more in the project demonstration. So basically, in the diagram on the left side, I have calculated the bit error rate for different values of signal to noise ratio. So basically, I had an array of signal to noise ratio values, and for each value, I calculated a bit error rate, and therefore, I was able to plot the bit error rate for different values of signal to noise ratio. For example, in this case, I started the SNR value from 0 to 15, and based on that, I had different values of bit error rate, and I plotted them in MATLAB. And the right side, I can see a command window. So this is basically a Reed-Solomon encoder and decoder use, and I have displayed the bit error rate, total number of errors, and total number of bits. So these are like two different MATLAB scripts for Reed-Solomon. And this is the result for LDPC code. Similarly, I have changed the values of signal to noise ratio, and I have calculated the bit error rate for different values of signal to noise ratio, and I have plotted them. And the right side, I can see a output for the LDPC encoder and decoder. This is a separate MATLAB script. Similarly, for turbo code, I have like plotted bit error rate versus EB by N naught for turbo code and uncoded signal. So I change the values of EB upon N naught from -5 to -1, and I have plotted the turbo code and uncoded signal. So you can see the difference between turbo code and the uncoded signal. If the value of EB by N naught decreases, the bit error rate in case of turbo code decreases, and the uncoded signal generally remains the same. And on the right side, there's a separate script for the turbo code encoder and decoder. This is the MATLAB output for that. I will explain all this in the project demonstration. So this is the result section for the BCH code. I have calculated the bit error rate for different values of signal to noise ratio. Similarly, I have varied the values for signal to noise ratio, and I have calculated the bit error rate for each of these values, and therefore I was able to plot this in the MATLAB script. And on the right side, you can see the bit BCH code encoder and decoder. The BER value came out to be this one for a particular signal to noise ratio. So this is for the convolution code, EB bit error rate to signal to noise ratio, and the command window on the right side. So the conclusion of this would be that it would be very unreasonable to conclude that a particular error correcting code can work for all kind of applications, because the use of an error correcting code depends on many factors like channel noise, simplicity, latency, type of errors, performance, and the hardware which is involved. And based on these factors, different applications use different codes. A particular code is not used for all applications. And for example, ARQ is widely used in network protocols for reliable communication, and we need a back channel communication in this case to mention if it was a positive acknowledgement or negative acknowledgement. The receiver sends this to the transmitter. Reed-Solomon codes and BCH codes are widely used in storage devices like solid-state device, DVD, CD, and ROM. And BCH codes are also used in 2D barcodes. LDPC codes, turbo codes, and Reed-Solomon codes are used for satellite and deep space communications. And turbo codes are competing with LDPC codes for high-end applications. So now I'll show you the project which is in MATLAB. So I have used MATLAB version 2016 for my code, and on the left side you can see that I have developed around 9 scripts in MATLAB for these kind of error correction codes and plotting their results in charts, which you saw earlier. So initially I'll show you a BCH code encoder and decoder. So initially I have cleared the console and cleared the number of variables on the left side, and rate of error variable is used to maintain the error statistics to find out the bit error rate, total number of errors. I'll show you how I do this in the end. Then I create a BCH encoder and BCH decoder. I am using a DPSK modulation in this case, and the bit input I'm setting as true. That means the input which is being sent to this is in the bit form, in a binary form. And then I'm creating a additive white Gaussian noise channel. And so basically this will mimic a normal day-to-day situation, and I can set a particular noise level in this case, or I can vary the noise level to probably show you how bit error rate changes with the signal to noise value. So in this case, I am setting the value of noise method to signal to noise ratio, and the value of SNR to be 10. So I am checking currently for 40 frames. So in each for loop, I am creating a random binary data, the value of which varies from 0 to 1. And this I have to send in a column vector form. That is why I have mentioned the number of columns to be 40 and number of rows to be 1. So this is a random data which I have created, random binary data. I have encoded this random binary data using a BCH encoder in this line. Then I am performing a modulation, DPSK modulation on this. Then I'm sending this through a white Gaussian noise channel. And this is the data I have received after it has been sent through white Gaussian noise channel. And there is a certain amount of noise in that channel. I have set the SNR value to be 10. Then I perform demodulation using DPSK. Then I'll decode using BCH decoder. So this is the final output I have received after encoding, decoding, and after the noise was introduced. So using this step, I'm comparing the data which I sent and data which I decoded. This is I've stored in the final output. And I'm checking this for 40 frames so as to generalize all this, and so as no statistical error was introduced. And so final output 0 will show the bit error rate, final output 1 would show a total number of errors, and final output 3 would show total number of bits. I'll just run this code. Yeah, so in this case bit error rate was turned out to be 0.008766. Total number of errors introduced were 14 and total number of bits were 1600. So if I run it again, the results would vary a little. Yeah, so you can see. Next I'll show you LDPC MATLAB script. So similarly I'm clearing the console and the variables on the left side, and rate of error is used to maintain the error statistics. So over here I'm creating LDPC encoders and decoders. Again I'm using an additive white Gaussian noise channel, and I'm using QPSK modulator and demodulator in this case. So I'm checking for 15 frames in this case, and this statement will create a random binary data with 32,400 columns and one row. So this is the column vector form, because LDPC encoder takes the data in a column vector form. So in this statement, I have encoded the data in using LDPC encoder. Then in this statement, I have performed DPSK modulation. This is the data which I have received after it has been sent to AWGN noise. Then I perform demodulation, and here I get the decoded data. So I'm comparing data which I sent and decoded, and I'm storing this in final output. I'm doing this for 15 frames so as not to introduce any statistical error. So if I run this code, yeah, I've run the code, and final output 0 will contain the bit error rate, final output 2 will contain total number of errors, and final output 3 have total number of bits. So in this case, bit error rate turned out to be 0.000004, and total number of errors were 2, total number of bits were 48,500, 4,85,997. Then I'll show you Reed Solomon encoder decoder. So similarly, I'll just clear the console and the errors. In this statement, I have created the Reed Solomon encoder and decoder. I'm using DPSK modulation with bit input set to false. So this time I won't be sending binary data. I would be sending random data from 0 to 7 in column vector form. I'll be using AWGN channel. So initially in this statement, I'll check for 40 frames. So in this statement, I'm creating a random data from 0 to 7. I have encoded using Reed Solomon encoder. Then I'll perform DPSK modulation. Then I'll send this through additive white Gaussian noise channel with SNR value set to 10. Then I'll perform demodulation and decode using Reed-Solomon decoder. In the final output, I'll compare the data which I sent and data which I received. And this final output, I'll display it over here outside. I'll check this for 40 frames, and BER turned out to be 0.103592, and total number of errors were 124. I'll run this again. Yeah, so the data changes a little bit. Now I'll show you turbo code. So for turbo code, EBN0 value I have set to -2, and for interleaver indices, I am creating random indices till 256. And over here, I am creating turbo code encoder and turbo code decoders. I am using BPSK modulation in this case. And for AWGN channel, I am sending the EBN0, I'm setting the value to this value. I'm checking this for 300 frames. So initially, I'll create a binary data using this function, random binary data. I've just run the output, yeah. So I'm using Reed-Solomon encoder in this line. Then I'll perform DPSK modulation. Then I'll send this to AWGN channel. Then I'll perform demodulation, decoding, and final output. So final output in this case turned out to be 0.005834. I'll run it again. Yeah, so a little bit of change. Then I'll discuss this Viterbi demodulation and convolution using convolutional encoder. So rate of error is used for statistics. I'm using convolutional encoder and Viterbi decoder, and I'm using DPSK modulator in this case with bit output set to true. That is, I'll be using binary data in this case. And for AWGN channel, so initially I'm checking for 20 frames. I am creating a random data from 0 to 1 for as in 30 columns would be there. Then I'll be encoding this using a convolutional encoder, and then sending this through AWGN channel and demodulating, then decoding, and this is the final output. So I'm doing this 20 times. I'll just run it. Yeah, so this is the output over here. So the output BER turned out to be 0.507 and number of errors were 303. Yeah, so the SNR value is very high in this case. It's turned out to be 10. So these are the files, MATLAB scripts in the chart folder which I've used to compare BER values to the SNR values for BCH, LDP, Reed-Solomon, and turbo codes. I have analyzed this in my final report and showed the results earlier also. So in this case, I'm using a BCH encoder and DPSK modulation. So SNR values I have stored in an array. So basically the first element is 10 and I'm incrementing 1 by each time. So the array would turn out to be values would have, I'll show you an example, somewhat like this 0, 1, 2, 3 till 10. So the first value is 0, last value is 10, and I'm incrementing by 1. So SNR values, I'm putting a certain range to that, and for each SNR value, I'll calculate the bit error rate value, and I'll store this in a new array, and then I'll plot the SNR values versus the bit error rate values. So for each SNR value over here, I have changed the SNR in the AWGN channel to the SNR value over here. Then I'll start a while loop for number of errors less than equal to 1000 and number of bits less than equal to this value. So I've done this so as not to introduce any statistical and varying errors each time I run the code. So I'll check till 1000 errors. I'll get a BER value for a particular SNR value. So I'm creating random data in this line, then BCH encoder, then modulation. Then I'll receive this data through AWGN channel, then demodulation and decoding. So I'm storing the BER value in this one, and I'm just plotting this in the end. I'll just run this code. Yeah, so this is the graph which I see, chart which I see. So for these SNR values, I have these BER values for BCH code. So I varied the values from 0 to 10, like I showed you earlier. And for each of these values, I got these values for bit error rate. Now I'll show you LDPC code, LDPC chart. So I'm using LDPC encoder and decoder over here, and I'll be using AWGN channel. I'll be using a QPSK modulator and demodulator. So again, I'll change the SNR values from 0.0 to 0.8, and each time I'll increment by 0.1. So the values would be like 0, 0.1, 0.2, somewhat like that, until 0.8. So for each of these SNR value, I'll find out the bit error rate value. I'll store this in an array. I'll plot this in the end. So for each SNR value, I'm setting the value in AWGN channel. Then I'll follow the same steps. I'll perform LDPC encoder, DPSK modulation, QPSK modulation, and then AWGN channel, then demodulation, decoding, and I'll store the final PER value. I'll do this loop for 250 errors. I did a trial and error in this case because if I increase this value a lot, then the code was taking a lot of time. So I've just run the output. So in the end, I have the SNR values and the BER values. I'll just display this in a chart. Yeah, so this is the result which I got for 0 to 0.8. I'm incrementing by 1 each time. So for these SNR values, I got BER values, and you can see the performance of LDPC code in this case very easily. Now I'll show you Reed-Solomon code. I'm using a RS encoder and decoder in this case. I'm using DPSK modulation and AWGN channel. I'm varying SNR values from 1 to 15. That is, value would be 1 to 0, 1, 2, 3, 4, 5 till 15. Let's run this code meantime. And I'm creating a MTBER array which I'll use to store the values in the end. So for final output number of errors, I'm setting this out to be like 100,000 something. I'm creating random data from 0 to 7. Then I'm using Reed-Solomon encoder. Then I'm using DPSK modulation. Then I'm sending this through AWGN channel. Then I'll be using a DPSK demodulator. Yeah, so this is the result which I got. I'll just explain this to you later. So the final output, I'll just store this in an array, BER values, and I'll plot this in the end. So this is the result which I got. So these are like SNR values over here from 0 to 15, and these are the bit error rate values on the left side. So for each SNR value, I got a different bit error rate value, and you can see easily the performance. As the value of SNR increases, the BER goes down for Reed-Solomon code. Now I'll show you turbo code performance. So for EBN0 values, I'm ranging from -5 to -1, and I'll be calculating the values of bit error rate. Again, I'll set out the loop for EBN0 values. I'll just run this. And for each of these values, I'll find the number of errors. For certain number of errors, I'll find the bit error rate so as not to include a statistical error. So over here, you can see that I'm using turbo code encoder and turbo decoder in the end. Yeah, over here. So initially, I'm creating a random data from 0 to 1, and I'm creating random interleaver indices in this case till the length of the frame. Then I'll perform demodulation. Data received uh, is through AWGN channel. Then I'll perform demodulation in the end, and I'll decode. Then I'll compare this to the data which I sent initially. So I'll compare both of them to see what were the differences after I send it through a noisy channel. So in the end, I'll display the values of EBN0 bit error rate for the turbo code, and also I'll also show uncoded version just to show a comparison how good a turbo code works. So the output is currently running, and it would like come out momentarily. And I'm using a 16QAM modulator and demodulator in this case. So like earlier, I am changing the values of I'm changing the number of EB N0 values. For each of these values, I am getting a different bit error rate, which I'll show you the plot in the end. So turbo codes are a bit slow in this case because number of outputs I'm expecting, number of errors is a bit more for this code. Yeah, so here is the output. So clearly you can see EB by N0 to BER values comparison over here. So the blue one is the turbo code, and the other one, the brown one, is the uncoded version. So you can easily see the difference in the performance between both of them. So these like charts show you the performance of these codes, BER versus SNR, and for turbo code, I have compared turbo code to the encoded version. I have also showed you the encoding and decoding of these error correction codes. I have also showed you a convolutional code using a Viterbi dynamic programming decoder. So these are the MATLAB scripts which I'll submit, and for the detailed analysis, I have mentioned in my project report, and I have also mentioned the application of these codes and their shortcomings. So the detailed analysis of these codes are there in the project report. I have just gone through them briefly over here, how they were like implemented in the MATLAB code. Yeah, so this was my project demonstration. Yeah, thank you for watching.